Okay, let's, PAM is pulse amplitude modulation. So let's just talk briefly about what happens when you've got an analog signal and you want to somehow send it over a digital system, like some crazy thing, like sending voice over IP or something. I don't know, just weird stuff. Okay, anytime that we want to send an analog signal over a digital system, we have to sample it. So, for example, in this case, here's our analog signal is this curvy bit here, and what we do is sample it at regular intervals. And so at each one of these points, we determine what the amplitude is, and we keep track of that number just as an amplitude. This is 1 over Fs, where Fs is the sampling frequency. Whoops. Okay. So this is basically a time sequence of impulses. So they now have amplitudes of A, T1, A, T2, A, T3, and so forth, right? It's just a line of impulses that have amplitudes that are equal to what the analog signal was at that time. That's called pulse amplitude modulation. Nice thing about this is we could now interleave multiple signals even without doing anything beyond this, because now we could put like every other sample. If we had 2 Fs of bandwidth, we could put every other sample is a separate channel, and so we could interleave 2 analog signals, which you can't do if you just have analog signals. You try and interleave them, they just add to each other, and everything's a mess. Okay, so that's pulse amplitude modulation. So what we end up with is this sampled analog signal, which is a series of pulses that represent the amplitudes of the original analog signal. So to reconstruct it, we use an integrator, which means that it, theoretically at least, it's an RC circuit that would theoretically charge up the capacitor to a certain level and then keep it there. In practice, capacitors leak, so it tends to drop just a little bit. But what we get here is something that looks kind of like the analog signal, only much blockier and jagged. Then we low-pass filter it so that it's not as jagged, right? Remember, sharp edges are high frequencies, so if we low-pass filter something, that smooths it out. So we use an integrator so that instead of just being pulses, it'll be levels at those levels, and then we use a low-pass filter to smooth it back out so that it looks kind of like the analog signal again. All right, so does the reconstructed amplitude of T look like the original? Not so much. Okay. Number one, it depends on the relationship of the spectrum and the sampling frequency. If we sample it, okay, so our bandwidth of A of T is someplace between its highest frequency and its lowest frequency, right? A of T has some highest frequency component that we're going to call F of H. Then our sampling frequency, Fs, is just 1 over the difference between the time intervals. Sampling frequency is just how often we set these pulses. So it depends on the relationship between A's highest frequency and our sampling frequency. How fast do you think we would have to sample it to reconstruct the signal relatively faithfully?
Mike was there, twice as much.
Okay. Twice as much. We have 1 vote for twice as fast. Anybody else? What if it was the same?
It was the same, like same frequency as sample?
Yeah, if we sampled it at the same frequency as our analog signal.
It'd be at the same frequency.
Well, first off, let's just check and see what happens if we do that. Let's say we have an analog signal that here, this is F, some F of C. And we want to sample it at that same frequency, F of C, right?
So it'd be the same.
So we would sample here, then we would sample here. Oh wait, no, sorry, here. I drew a sample and a half here. And then we would sample here. Hey, it would just be 0. Okay, that pretty much wouldn't work. If we sampled at lower frequency than this frequency, we're going to get some random stuff. So, okay, so we know that it won't work if fs equals fh, and we can be pretty safe in saying if it won't work there, it won't work at any lower frequency. So yeah, it needs to be bigger. Cab Sherburne has says twice as big. Anybody say it needs to be bigger than that? 10 times?
Twice, more than twice.
More than twice as big?
Would twice get you the
All right. Okay, so this was that was actually a big question, and it fell to Mr. Theorem to come up with Nyquist's sampling theorem. Oh, actually, it possibly could have been Nyquist himself. Hold on, let's see if... sadly, unlike most of our famous mathematician types, oh, come on, this thing's so slow when it's... Unfortunately, he has no interesting facial hair. He's just a dude. That was Harry Nyquist. He came up with this idea that analog signal can be perfectly reconstructed if the rate at which the signal is sampled is more than twice the highest frequency component in the original signal. So, Cab Sherburne is right. Actually, though, it's strictly greater. It's more than twice, so it has to be greater than twice the highest frequency. So Nyquist's sampling theorem says if fs is a sampling frequency and fh is the highest frequency component, then fs has to be greater than 2fh. So that's Nyquist's theorem. We can go through the proof here. Basically, what I want to show, though, is when you sample something, in the frequency domain, it has copies of it at multiples of the sampling frequency. Okay, that's just an artifact of taking the Fourier theorem. Now, so we have room from 0 to fs in here, right? This triangle represents the analog signal, so its highest frequency, fh, is right here. So fh, there's a positive version and a negative version. So we've got from 0 to fh is full, and from fs down fh is full. So we've got two fh's there taking up space in the middle of that fs, right? Does that make sense? Yeah, I know. As I was saying that. Okay, so this... Whoops. No, that's terrible. That goes from 0. This is fh right here, right? Then centered on fs, we have another copy. So this is fs plus fh. That's supposed to be a plus, not a... And this is minus fh over here, right? Because this is an exact copy of our original. So here's the issue, that we've got this part of it takes up fh right there, right? And this part of this one takes up fh. So altogether, these two halves take up 2fh. Now, if fs is not big enough, then that 2fh is going to overlap. So fs has to be greater than 2fh, or those will overlap. Does that make sense? Because, yeah, if there's not enough room for two fh's to fit in there, then they're going to overlap like this. And that's what Nyquist basically shows.
Does that benefit us exactly?
Well, that doesn't. That's actually not a benefit. What we want to be able to do in the end is reconstruct our original signal, which is. Let me do this in a different color. Which is this right here, right? We can do that. We've got all these extra copies of it, but we can get the original back by just low pass filtering right here. But if this is overlapping and we low pass filter right there, we get that plus some overlapping stuff right here. So it messes it up. So that's what we're trying to say here, is that if Fs is not more than 2FH, we get what's called aliasing, which means we get overlapping of the signal and its copies of itself, which screws us up. So we have to be sure that these tails don't overlap like this, right? Everybody see how that works? Okay. All right, so this is called aliasing. We have one new definition. Our Nyquist frequency is 1/2 Fs. So let's do it. Let's do a little example. If I have a signal that has a high frequency component, its highest frequency FH is 8 kilohertz. We need to sample at how much? Greater than 16, right? So we should have Fs is greater than 16 kilohertz. Now let's say, just for the sake of argument, that I sample it at 15 kilohertz. What's my Nyquist frequency?
7.5 kilohertz.
All right, my Nyquist frequency is 7.5 kilohertz. But wait, that's less than the high frequency. Shouldn't it be 8? Well, it should be 8, but it's not, right? Nyquist frequency is just defined by the sampling frequency. So it's 1/2 Fs, and now we can recast Nyquist theorem as Fn has to be greater than Fh, right? So Fs is greater than 2Fh, which means Fn has to be greater than Fh. If A of t has any frequencies above Fn, then the sampled signal is going to get reconstructed wrong.
What's that D again?
Just any component of A that's greater than Fn.
Okay.
Okay, so any frequency F or Fc above Fn is going to screw it up. So power at Fc aliases to a false component at some other Fa, some frequency less than Fn, which is just a mirrored around, it's the difference mirrored around Fn, which just adds to existing power as noise. And I'll show you a picture about that. So if Fc is delta F above Fn, then Fc equals Fn plus delta F, right?
Mm-hmm.
Let me draw a little picture just to make this clearer. Here's frequency. Here's Fn. Let's say that our analog signal hung over Fn a little bit, right? And so we have power all the way up to Fc here. So this difference here is delta F.
And Fc will always be contained within Fh, it won't be higher.
Right,
It won't be a
Fc, you're
component.
right, Fc is always someplace less than Fh.
Okay.
Okay, so what's going to happen here, you'll notice if we do this, here's 0, we have Fa, then here's Fs, here was our Fn, and it hung over, so now we're gonna get overlap like that, right? So if you sum these together and then cut it back off here at Fn, result, different color. Our result here is going to all look right till right there, but,
Why are you,
and then it's going to have.
why are you saying FN is that little crossover?
Oh, because at the Nyquist frequency, Fn is half of F8, Fs, right?
Someone chose a bad FS.
What's that?
Someone chose a bad FS.
Yeah, this is an Fs that's too small, right? A good solution would be 0 Fn Fs, and then we had something like this. Then it just gets mirrored at Fs. Then when we cut it off again at the end,
Oh, okay.
ta-da, everything works fine. So this is if, because this is FH, right? So in this case, Fs is greater than 2 FH, or in other words, Fn is greater than FH. In this case, Fn is less than or equal to FH.
Really like demonstrate this using like a waveform and not these triangles that I don't really understand.
Everybody loves triangle. Yeah, I will show this to you. You can't really see it in the time domain very easily, but tomorrow I will try and find a way to show it in the time domain with some waveforms. So anyway, I'm just showing you what happens is we get this aliasing, and then we'll work on that tomorrow since it's lunchtime. So have a good lunch. In the meantime, will print out homework 2 and